So we've already learned about polar and nonpolar bonds. Now we're going to learn about polar and nonpolar molecules. So the word polar means opposite ends. So we can have bonds that have opposite ends or not. Likewise, we can have molecules that have opposite ends or not. By opposite ends, we're talking about regions of partial negative charge. If the electrons are more on one side of a molecule than another, that'll make that molecule polar. And if the electrons are not on opposite ends, if they're found in the middle, let's say, of the molecule mostly, or between, right in the middle between two atoms, then that molecule will be nonpolar. So two reasons that molecules can be nonpolar. One is based on the geometry of the molecule. So by geometry, I mean this. If a molecule is symmetrical, then that molecule will be nonpolar. A symmetrical molecule is one in which everything attached to the central atom is the same. We'll see examples of this in just a bit. Another reason molecules can be nonpolar is based on the polarity of the bonds in the molecule. This is especially important when we're looking at molecules that are made of just two total atoms. So if the one bond in that molecule is nonpolar, then the molecule as a whole also then is nonpolar. So let's take a look at some examples. First one is nitrogen. If we look at the Lewis structure for nitrogen, nitrogen has two atoms only in that molecule, one bond, even though it's a triple bond. And how would you describe the bond between the nitrogens? That bond is a nonpolar covalent bond. And since the one and only bond in that molecule is nonpolar, the molecule as a whole is nonpolar. And so we'll see that with any of the diatomic molecules. Same thing with chlorine. The one and only bond in this molecule is nonpolar. Therefore, the molecule as a whole is polar. Now be careful. Don't think that because a molecule has polar bonds that it's polar, or if a molecule has nonpolar bonds, it's nonpolar. It's not always the case. So you need to be careful. Again, if we look at letter A, the geometry of the molecule also can make a molecule nonpolar. For example, let's look at one we've drawn before, Lewis structure for carbon tetrachloride. Looks like this. Let's see if I can squeeze this in there. So a little different situation if the molecule is made of more than just two total atoms. So we have to look at the arrangement of the atoms around the central atom. So is this molecule symmetrical? Now again, I don't mean symmetrical in the context of like geometry. A symmetrical molecule is a molecule in which everything attached to the central atom is the same. So what exactly is attached to the central atom in this molecule? We have 4 chlorines. And because everything attached to the central atom is the same, this molecule is symmetrical. Therefore, it is nonpolar. Now, something that's important to see here is that this molecule, even though it is nonpolar, it does have polar bonds. So all 4 of those bonds in that molecule are polar, but because of how the bonds are arranged around the central atom, the molecule as a whole is nonpolar. Let's take a look at another example. Go ahead and draw the Lewis structure for carbon dioxide. So it looks like that. So this molecule, like carbon tetrachloride, also contains polar bonds. But what's attached to the central atom? We have 2 oxygens. This molecule is symmetrical and therefore is nonpolar. All right, how about polar molecules? Molecules can be polar because of one of 2 reasons. One, the arrangement of the atoms around the central atom, or the geometry. And then 2, the polarity of the bonds in the molecule. Again, this is important when we're looking at molecules that have just one total bond. For example, let's look at, here, I'm going to have you actually do these. So go ahead and draw the Lewis structure for carbon monoxide. Pause the video now. So carbon monoxide has a polar covalent bond, and since the one bond in that molecule is polar, the molecule as a whole is also polar. Next, go ahead and draw the Lewis structure for ammonia. Pause the video now. So there's the Lewis structure for ammonia. Let's go back to carbon monoxide for a second. Oxygen is more electronegative than carbon, and so the oxygen end of the molecule is slightly negative, and the carbon end of the molecule is slightly positive. So we have a molecule with opposite ends. Right, ammonia. What is attached to the central atom? Tell me. All right, so here's how it works. If you use the word "and" when describing what's attached to the central atom, that molecule is not symmetrical, and if it's not symmetrical, it will be polar. So in this molecule, we have 3 hydrogens and 1 lone pair. This molecule is not symmetrical, therefore it is polar. Now, if we look at the bonds in this molecule, nitrogen is more electronegative than hydrogen. The shared electrons are pulled towards nitrogen's nucleus, giving the nitrogen end of that molecule a partial negative charge, and the hydrogen end of the molecule a partial positive charge. Instead of arrows, we don't use these both together, but instead of arrows, we can do delta negative on the nitrogen end of the molecule and delta positive on the hydrogen end of the molecule. All right, let's try one more. Go ahead and draw the Lewis structure for chloromethane, CH3Cl. Carbon is a central atom. Everything else is attached to the central atom. Go ahead and pause the video now. So here's the Lewis structure. If your chlorine is on the left side or on the top or on the bottom, that's fine as long as there's 1 chlorine attached to the carbon. All right, so what is attached to the central atom? We have 3 hydrogens and 1 chlorine. So this molecule is not symmetrical, therefore it is polar. All right, in summary, molecules are usually polar to some degree if there are lone pairs of electrons on the central atom, we saw that with ammonia, or there are different attached atoms to the central atom, like we saw in chloromethane. Now be careful, there's 2 exceptions to number 1 there, where you have molecules that have a lone pair of electrons on the central atom but are nonpolar. The 2 exceptions are the linear derivative of the trigonal bipyramidal geometry, so that's AX2E3. Looks like this again. Oops, let's try that again. So the bonds cancel each other out, and these lone pair of electrons, remember they occupy the 3 equatorial positions around the central atom, they cancel each other out as well in terms of them pulling, or having electron density, we call it, around the central atom. So this molecule would be nonpolar. The other example is square planar. So we have a derivative of the octahedral geometry. Looks like this. The bonds all cancel each other out, meaning they're kind of pulling all in opposite directions. And then those lone pair of electrons, one on top, one on bottom of the central atom, if you will, and those axial positions also cancel each other out. So this molecule, square planar, would also be nonpolar, even though it has a lone pair of electrons on the central atom. So let's do this. Go back to your Lewis structures. We labeled molecular geometries for each. Let's label polarity of each. And we're going to label one more thing, so hopefully I have room for 2 more things to fill out here. Carbon tetrachloride, you have 4 chlorines attached to the central atom. This is symmetrical. It is nonpolar. NF3, 3 fluorines and 1 lone pair. It is polar. H2SE, we have 2 hydrogens and 2 lone pairs. That molecule also polar. F2O2 and N2, all of them have nonpolar covalent bonds. It is the only bond in the molecule. Therefore, all 3 of those are nonpolar. We don't do polarity for polyatomic ions, so we'll skip the NF4 plus and the SO3 minus 2. So let's go to SO3, sulfur trioxide. You have 3 oxygens attached to the central atom. This molecule is symmetrical, therefore it is non-polar. BeCl2, 2 chlorines. Molecule is symmetrical, non-polar. ICl3, 3 chlorines and 2 lone pairs. That molecule is polar. C2H6, actually everything attached to the carbons is the same. So C2H6 is actually a non-polar molecule as well. SO2, 2 oxygens and 1 lone pair. That molecule is polar. XeF4, 4 fluorines and 2 lone pairs. This molecule is non-polar. It's one of the exceptions, so be careful. Got a lone pair of electrons there, but it is non-polar. What is the purpose of polarity? Why is polarity important? Well, it determines what type of intermolecular forces, we call them, occur between molecules. So that's prefix inter means between molecules, forces of attraction between molecules. For example, you have some water. Water is made up of water molecules. What is holding all of the H2Os together? Well, what's holding the H to the O are covalent bonds, but what's holding the H2O to other H2Os is some type of intermolecular force. There are 3 types of intermolecular forces. First one are known as dispersion forces or London dispersion forces. London named after a person, not after the city. So that's why sometimes I'll abbreviate it LDF, London dispersion forces. London dispersion forces occur when a particle has its electrons shift from side to side. And this creates something called an instantaneous or temporary dipole. Dipole is another word for polar. Di means 2, pole ends, so 2 ends, a dipole. So you have a molecule that is temporarily and ever so slightly polar. I'll show you how this happens in just a second. This is going to have a domino effect, causing the particle next to it to do the same thing. Let me show you what I'm talking about. So let's take a look at this molecule. So let's go back to our tug of war analogy. So when you have 2 evenly matched teams playing tug of war, what happens to the flag that's in the middle of the rope? Well, it doesn't just stay right in the middle of the 2 teams. One team pulls a little bit harder and the flag goes closer to their team, and then the other team pulls a little bit harder and the flag goes close to their team, and that flag moves from side to side. On average, it's right in the middle of the 2 teams, but it does move side to side. Same thing here with these 2 electrons that the chlorines are pulling on. The right chlorine may pull the electrons closer to its nucleus, and then the left one pulls them closer to its nucleus. And so I use that term instantaneous dipole for a very brief moment in time, because those electrons, shared electrons, are more on one side of the molecule than the other. It makes the molecule ever so slightly polar. All right, so let's say we have another chlorine molecule next to it. So we don't just have a chlorine molecule by itself. Imagine you have a container full of chlorine gas, and so you have all these molecules together. Well, what's going to happen? So we have electrons here on the right side of this molecule. What are they going to do to these 2 electrons here between these chlorine atoms? Well, what do like charges do to each other? Do like charges attract? No, like charges repel. So what's going to happen is it's going to push these electrons away or towards the right, making this molecule ever so slightly polar as well. Now, what do you notice about the right side of the chlorine molecule on the left and the left side of the chlorine molecule on the right? I'm talking about here and here. We have partial negative, partial positive. What do opposite charges do? Opposite charges attract. Sometimes we show that attraction with a dotted line or kind of a dashed line like I did here. That attraction between those ever so slightly or temporarily polar molecules is called a dispersion force. And has to do with those electrons in those molecules moving around and moving from side to side. All right, this force occurs between everything. All molecules and atoms exhibit dispersion forces, whether they're polar or nonpolar, doesn't matter. So everything has dispersion forces. The strength of dispersion forces varies. On average, dispersion forces are the weakest type of attractive force. When we're talking about all attractive forces, we're talking about all these intermolecular forces, ionic bonds, covalent bonds, metallic bonds. Dispersion forces are the weakest on average. Sometimes they can be pretty strong though. So dispersion forces increases when a particle is larger. So if you have a larger atom and a smaller atom, the larger atom is going to have stronger dispersion forces. Larger atoms, because they have electrons in higher energy levels, have larger electron clouds. The larger the electron cloud, the more polarizable that molecule or atom is. So this is a term we use in IB and AP, polarizability. The ability to become polar, where you have electrons more on one side of a molecule than on the other. Also, dispersion forces increase, the strength of dispersion forces increase when a particle is longer. For example, if you have this molecule here, which is called ethane, compared to this molecule here, which is called propane. And since propane is a longer molecule, longer chain of carbons, its electron cloud is more polarizable, giving propane stronger dispersion forces than ethane. All right, dipole-dipole forces. Again, the word dipole means polar molecule. So dipole-dipole forces occur between not temporary dipoles, but permanent dipoles. Not molecules that are temporarily polar, but are always polar. Dipole-dipole forces are usually stronger than dispersion forces if we're comparing molecules that are about the same size. Nevertheless, dipole-dipole forces are very, very weak when compared to covalent and ionic bonds. Only about 1% as strong as a covalent or ionic bond. So that gives you an idea of how strong covalent and ionic bonds are. Take a look on table 14.2 in your books. It kind of summarizes the difference between dispersion forces and dipole-dipole forces. Notice it mentions boiling points and melting points. So substances that have stronger attractive forces will have higher melting points and boiling points. And so we can see that there with the examples given in the book. Even comparing nonpolar molecules to each other, like oxygen and fluorine. We have bromine there as well. Notice that bromine's melting point is significantly higher than both oxygen and fluorine. -7 is much higher than -200 and something. So that's due to the fact that bromine molecules are larger than fluorine molecules and larger than oxygen molecules. And then we see a difference also with dipole-dipole forces. Their strengths vary a little bit as well. We're not going to get into that just yet, though. So let's take a look at an example of molecules that exhibit dipole-dipole forces. We'll look at the molecule hydrogen chloride. Chlorine is more electronegative than hydrogen. Let me just scooch this down a little bit because I have to write something else. All right, because the chlorine is more electronegative than hydrogen, it pulls the shared electrons towards its own nucleus, making the chlorine end of the molecule partially negative, the hydrogen end of the molecule partially positive. Well, what if there's another HCl molecule around? Well, how is it going to align itself or arrange itself relative to this one? It's going to align itself like this, where the hydrogen end of one molecule is close to the chlorine end of another molecule. Why is that? Well, because of this. So again, we see delta negative, delta positive. The attraction between the positive end of one molecule and the negative end of another polar molecule is called a dipole-dipole force. Force of attraction between dipoles or polar molecules. Got one more. Now be careful. Though it has the word bond in its name, this is not a type of chemical bond. Hydrogen bonding is a type of intermolecular force, force of attraction between molecules, not within. The prefix for within is intra. Intramolecular forces are called covalent bonds. We're not talking about that. We're looking at force of attraction between molecules. Hydrogen bonds occur between permanent dipoles. So this occurs between polar molecules. However, it's a little bit different than dipole-dipole forces. So hydrogen bonding is an unusually strong dipole-dipole force. It doesn't occur just between polar molecules, but what I like to call superpolar molecules, molecules that are especially polar. And so the force of attraction between them is going to be especially stronger. So hydrogen bonding only occurs between molecules that have nitrogen, oxygen, or fluorine, change your notes a little bit, bonded to, of course, a hydrogen. So any molecule that has NH bonds or OH bonds or FH bonds will exhibit hydrogen bonding. Significantly stronger than dipole-dipole forces, about 5 to 10% though, as strong as covalent and ionic bonds. So still very, very, very weak compared to chemical bonds. So why is it stronger than dipole-dipole forces? A couple reasons. One, the large difference in electronegativity between the hydrogen and either the nitrogen, oxygen, or fluorine atoms. Likewise, due to the small sizes of the nitrogen, oxygen, fluorine, and hydrogen atoms. So let me give you an example of what's happening with hydrogen bonding. So I'll draw it up here because I'm out of room down below. So let's look at the molecule hydrogen fluoride. Fluorine is the most electronegative element, way more electronegative than hydrogen. So fluorine is going to pull these shared electrons towards its own nucleus. Actually, I don't know. I'm going to do this where I have more room because I got to show you something else. So let's do this. All right, HF is not just a polar molecule, it is superpolar. So notice how I drew the deltas here versus with HCl. I'm trying to show you that HF is a more polar molecule than HCl. So if we have another HF molecule, it's going to arrange itself like this. So the attraction between the fluorine end of one molecule and the hydrogen end of another molecule is called a hydrogen bond, an especially strong force of attraction between polar molecules. All right, in summary, a molecule that is nonpolar will only exhibit dispersion forces. So the only force of attraction between nonpolar molecules are dispersion forces. For polar molecules, they will exhibit dispersion forces, of course, and either. It can't be all three. Dispersion forces along with either dipole-dipole forces or hydrogen bonding. It cannot be dipole-dipole and hydrogen bonding. That doesn't make sense because they're kind of similar. And so it's either polar molecules attracted to each other, that's dipole-dipole, or very polar molecules attracted to each other, that would be hydrogen bonding. So let's do this again. Let's go back to our Lewis structures. And I have some additional examples for you as well, but let's go back to our Lewis structures and predict the type of intermolecular forces that occur between each of those molecules. All right, we said CCl4 is nonpolar. Since it's nonpolar, it will exhibit dispersion forces only. NF3 is polar. If it's a polar molecule, here's what you need to do. Does the molecule, first of all, have hydrogen in it? And is that hydrogen bonded to NO or F? If the answer is no, it does not have hydrogen, or the hydrogen is not bonded to NO or F, it's not hydrogen bonding, it must be dipole-dipole. So here, this molecule does not have hydrogen, but it is polar, so dipole-dipole. H2SC has hydrogen. Again, just because it has hydrogen does not mean it has hydrogen bonding. The hydrogen in this molecule is not bonded to NO or F, so this molecule has dipole-dipole forces. F2O2N2, they're all nonpolar, therefore they all exhibit just dispersion forces. Oh, I skipped some earlier. I just realized that. All right, BF3 is nonpolar. It's a symmetrical molecule. Therefore, it will exhibit just dispersion forces. SeCl6, also symmetrical, also nonpolar, also dispersion forces. PF5, also symmetrical, also nonpolar, also dispersion forces. So everything on this slide exhibits just dispersion forces. They're all nonpolar. We don't do polarity or intermolecular forces for ions, so we'll skip those. SO3 is nonpolar, therefore dispersion forces only. BeCl2, nonpolar dispersion. C2H6, nonpolar dispersion forces. XeF4, nonpolar dispersion forces. ICl3 does not have hydrogen, therefore it does not have hydrogen bonding. It must be then dipole-dipole since that molecule is polar. SO2, polar, no hydrogen, therefore dipole-dipole forces. Here are some additional ones we drew, so flip back to that page in the notes. CO is a polar molecule. No hydrogen though, so dipole-dipole. NH3 is polar, has hydrogen, and it is bonded to, in this case, nitrogen, so that has hydrogen bonding. CH3Cl, polar molecule, has hydrogen, but not bonded to NO or F. That molecule will exhibit dipole-dipole forces. All right, so that concludes this lesson and this unit. Thanks for watching.